All right, Jacob, if you would turn off that light for me, please, sir. Okay, so how was everybody's 3-day weekend? Good? Okay. Just a couple things. The biggest idea is going to be on Monday the 28th. We have our next exam, and it covers just everything we've been talking about as far as probability. We should be able to finish up the current lesson. If not today, then definitely by tomorrow, get the majority of that done, and then we can just spend the rest of the days practicing. You've got your assignment. That's going to be due on Friday, so hopefully once everything's said and done, we can run through it the same way we did the previous lesson. But on this, I'm going to allow you to use a 3x5 index card. All right, so it's got to be an index card, not a piece of paper that's 3x5 you cut out. But whatever you want to write on it, front and back, it's fair game. Okay, so if you want to write anything on there that could help you dealing with probability, okay, it's completely up to you, but you have that option. The majority of the other items are for pre-calculus. I just want to make sure I don't miss anything. Tomorrow morning is the deadline if you want to retake the first exam. Let's see, that doesn't apply to us, that doesn't apply to us. Next week, I'll go ahead and give you an idea about this. Not this week, but next week, there won't be any morning tutorials. The 28th to the 1st, through the end of the 6 weeks. That's when they have me doing morning duty. I think I'm going to be walking around the dining hall, so if you do need me, I'll be walking around there. But next week, again, not this week, I'll be here after school from 3:55 to 4:20 for tutorials if anybody needs it. Also, something that's going to be happening tomorrow throughout the morning. Have you guys heard about the Stop the Bleeding training? Okay, does anybody need to know those times? I do have that. Okay, you do need to know the times? Okay. So let me pull this up very quickly. Stop the bleeding. Okay. So this is starting tomorrow morning. By law, all the students as well, I need to put it in the tray, have to be trained on this. And it looks like, according to the email, they're going to be training 40 students at a time. So the freshmen are going to be called down to the dining hall at 8:20. So basically, the class period you're called down into, looks like you're just pretty much going to miss that. Sophomores will be called down at 9:14, juniors at 10:08, and then seniors and anybody who missed one of the previous sessions would be 11:02 to 11:46. So that is not going to affect us tomorrow in the afternoon, but I just wanted to go ahead and make sure that you were aware that's happening tomorrow. Hello, sir. Okay, so that is happening. Also, while I was at Content Focus session yesterday, I was talking to one of the statistics teachers, and she had this website on correlation. Because remember, we had the idea that correlation does not mean what? Causation. But it's really interesting because a lot of people took the time for these different topics to compare the results they had collected. And I just wanted to go ahead and show you this very quickly. Like, here is U.S. spending on science, space, and technology versus suicides by hanging, strangulation, and suffocation. I mean, look how that almost lines up. That's really insane. I mean, now obviously one doesn't influence the other, but it's a really good idea. Causation correlation does not mean causation. Here's one here: number of people who drowned by falling into a pool versus films Nicolas Cage appeared in.
I don't know. I think that one might be on purpose.
You think that one might be on purpose? Oh, another Nick Cage film. I got to go visit the pool. Okay. This one was actually really interesting to me. Per capita cheese consumption versus the number of people who died by becoming tangled in their bed sheets. So that is a thing. That is a thing. So, I mean, and this is only a few of them. I thought I'd go ahead.
2008? Like, what were people doing?
It happens. I mean, people unfortunately die in ways you wouldn't consider. I mean, I don't know the statistic. I need to look it up, but there are a certain number of people who die every year from either a vending machine or a television falling on them. Because a lot of times, if, say, a vending machine doesn't work, people, grab it and start banging on it, and they fall back on people.
It's like the kind of stuff that happens to, like, Wile E. Coyote. Or
basically, yeah.
Like yeah.
Okay. But there are more than I'm just showing here. Would anybody be interested in looking at this? Okay, so I will go ahead and post this link to the website so you can take a look at it, because it really is interesting if you think about it. Okay. But there we go. All right. So let's get going. We have our first focus activity of the new set. Remember, we turned in numbers 1 through 4. Now, next Friday, the 1st, is the end of the grading period, so we've only got less than 2 weeks. I mean, this week is a short week itself. So we still have, several grades we're going to take, one of which is going to be another focus activity set. So I'll do one with you today. Maybe I can convince Mr. Yacht to go ahead and try the next one with you, but he has mentioned that statistics is not his strong point, so he may just go ahead and work a problem with you. But you'll get the 6th one on Thursday, and more than likely, because we're testing on Monday, I would say Tuesday, and then we'll turn them in probably on Wednesday of next week to go ahead and get one more grade in before the close of the grading period. So let's see what this one says. A hospital is trialing a new anesthetic drug and has collected data on how long the new and old drugs take before the patient becomes unconscious. So all of these represent time in seconds. They wish to know which drug acts faster and which is more reliable. Okay, so we've got the times for the old drug versus the times of the new drugs. Prepare a parallel box plot for the data sets and use it to compare the two drugs for speed and reliability. The 5 number summaries are, so it's been a while since we've heard that phrase, the 5 number summaries. That refers to your minimum value, Q sub 1, the what quartile? Lower quartile, the median, Q sub 3, which is the upper quartile, and then the maximum value. So why don't we go ahead, let's say that the old drug times, that's what I've labeled as the X here, just so I can have a difference between the two. So let's go ahead and do this by technology. We don't need to go ahead and do it by hand. Bless you. So I'm going to come on over here. Okay, let me go ahead and get rid of that. Document B. So I'm going to my home screen. How would I input data so I could see the scatter plot? Okay, so I'm going to go to number 1, list of spreadsheets. Okay, I'm going to go ahead and title it X, even though we know it's time. Remember, don't ever, put anything into the equals row. And now let's input the old drug times. So I've got 8, 12, what do we got here? 9, 8, 16, 10, 14, 7, 5, 21, 13, 10, 8, 10, 11, we got an 8, another 11, a 9, 11, and a 14. Excuse me. So there's 20 sets of data here. All right. Where do I go now? Okay, now remember, there is one thing I could do in order to go ahead and get that 5 number summary. Okay, so I'm going to go to menu. Where do I go? Statistics. Stat calculations. One variable, this is just one set of data. Even though I have 2 sets, I'm comparing them with separate graphs. So one variable, statistics. Okay. Number of lists, okay. Well, I'm going to go ahead and make sure the X list, it's titled at what I have there. Okay. Everything's going to be showing up in column C. I'm going to click OK. All right, so let's see here. If I go ahead and scroll up, okay, I'm going to have all the normal information. There's the mean, there's the standard deviation. But what I'm interested in is this 5 number summary. Okay, so there's the minimum to the maximum, lower and upper quartiles, the median. So 5, 8, 10, 12.5, and 21. So let me come on back over to my paper here. Okay, so it was 5, 8, 10. Was it 12.5? 12.5 and 21. There we go. Okay. Now, has anybody already had the opportunity to plug in the second set of data and already has the 5 number summary for that? Some of these we might be able to get just by looking at it. What's the smallest element in the new drug times? It was like 7 is the lowest. Okay, what's the maximum? 12. Okay. Now, if you were to go ahead and do this by hand or go ahead, plug it in technology just like we did the other one, you'd end up with a lower quartile of 8. The median is 9, and the upper quartile is 10. Okay. So I want to compare the results. When we're talking about parallel box plots, we're just going to go ahead and graph two box plots at the same time. Not overlapping, just one above the other. Okay, so why don't we go ahead and do the old first. So its lowest is 5, its largest is 21. Then we have a median at 10. We got a lower quartile at 8. And then 12.5 is the upper. So 12.5 would probably be right about here. Okay, so there's the box and whisker plot for the old drug. Let me go ahead and label this as old. All right. I'm sorry, ma'am? Okay. And then right above it, I'll just go ahead and plot the new drug box plot here. So let's say the lowest we have here is 7. The maximum is 12. Okay, and then the median is 9. Lower quartile is 8, and it looks like the other one is 10. Okay. Yes. Oh, maybe one above and one below? Oh, that'd be great. I'd be okay with that. Yeah. Okay. So there we go. And we really didn't talk about this aspect of box and whisker plots when we first started talking about them. But if anybody, as they're going through your internal assessment, sees a possible way to include this idea into that project, I mean, that's great. So let's say, based on what we have here, the question is, okay, based on the results, what would you say is the more reliable drug? Would it be the old or would it be the new? Okay, so a lot of people went ahead and said new. Okay, I would agree with you. I would go ahead and probably support that just based on a couple of characteristics I see. First off, what was the median time for the old drug for people falling asleep? Yeah, so 50% or less of the people using the old drug took 10 seconds to fall asleep, right? But with the new drug, 50% or less of the patients was able to do what? Fall asleep in 9 seconds. Okay. So half the patients were already able to fall asleep faster than the old drug. So that's one thing we could use as evidence. Also, another one, I would go ahead and maybe find the range. Just think of a couple of characteristics here. How do I find the range? There you go. Now, when we're saying range, this is the maximum value minus the minimum value. Well, how's that different from the IQR? What does IQR stand for? Interquartile range. So how do you find the IQR? There you go. The upper quartile Q3 minus the lower quartile Q1. So the range, I'll just put R on this one. So the range, the max 21 minus the minimum. Okay, for the old, what do we get? 21 minus 5. Okay, so 16. And 12 minus 7. So the range for the new drug is 5. Okay, so the range is just a measure of spread, right? So I'm seeing here that the measure of spread for the old drug is much larger than for the new drug. The times are much shorter. Okay, because the range is smaller for the new drug, I would also go ahead and use that as evidence that it's probably going to be more reliable than the old drug. Okay, questions? Okay. Did anybody have all 5 of those filled in, those blanks for each before we started? Okay, good. Did anybody do it by hand? No? Okay. Ella, you had a question?
Is it possible for the interquartile range to be like larger than okay.
It's possible. It just depends on the data. Because remember, what is a box and whisker plot actually doing with the data? It's dividing it up into quarters. Okay. So what it's saying is that between this first one was 5, right? And then it went to the lower quartile of 8. Okay. So between 5 and 8, that should represent 25% of the data. And then between the lower quartile and the median, that's 25%. And then that's what it's doing. So it is possible to have a much longer rectangle and shorter whiskers. It just depends on the values of your elements. Okay. All right. Any questions? Sounds good. Okay, we'll go ahead and put that to the side, somewhere safe where we won't lose it. Okay. And this is where we left off on Friday, I believe. Yeah, we actually had the opportunity to talk about conditional probability. And we went through several examples. We started the lesson, again, connecting probability to sets and Venn diagrams as we've seen previously. But this is what we were spending our time on this past Friday, conditional probability. Yes, ma'am? Friday. The assignment's due Friday. Okay. So conditional probability, put simply, is you're finding the probability of an event knowing that some other event has already occurred. And we were talking about how that changes your sample size. The first example we had here was the probability of rolling a 2 was 1 out of 6. But let's say, what's the probability of rolling a 2 given that you rolled an even number? So see, instead of looking at all 6 possible outcomes, you're only looking at 3. The sample space changed because on a fair die, there's only 3 possibilities for an even number. Okay, so here is the formula. Okay, that little line right there is A given B. Now remember, you always do it according to a numerator and denominator. You take the probability of the intersection of the 2 events divided by the probability of the given event. Whatever is given, that's what you go ahead and divide by, the probability of that event. Okay, so I think we finished up with this, right? Did we get to these? Okay, so these are some extra problems that are not in your notes that I was talking about last week. So let's go ahead and practice some of these. We'll practice one together, and then I'll give you the opportunity to go ahead and try one on your own. It says, in a class of 25 students, 14 like pizza and 16 like iced coffee. Okay, so let's say this is pizza, C for coffee. Okay, 1 student likes neither and 6 students like both. Okay, 1 student is randomly selected from the class. What's the probability that the student likes pizza given that he or she likes iced coffee? What's that key word when we're talking about conditional probability? Given. All right. Now, is it possible to have a conditional probability problem without having that word given? Okay, yes, and I'm going to show you some examples probably in the next day or so. All right, but how would I fill in this Venn diagram? How many is in the universe? 25. Okay, so U equals 25. So where would I start? Okay, 6 in the middle. We know that 6 people like both pizza and iced coffee. So the intersection, the overlap of the 2, I'm going to put 6. We know 1 person doesn't like either. So somewhere in the rectangle, outside those sets, I'm going to go ahead and put that 1 individual. Okay, well, now that we know the overlap, we can kind of just work our way out from that. How many people like pizza? Well, you're absolutely right. Only 8 people strictly like pizza. Of the 14, 6 like pizza and the iced coffee. Okay, does that make sense? Okay. Well, if I know that 16 people like iced coffee, then how many people like just the iced coffee? 10. Okay. So is everybody getting more comfortable filling in these Venn diagrams? Anybody confused? I mean, even though it's been quite a while since we've been talking about them, I mean, better latte than never. Iced coffee. Yeah, what? You knew it was coming? Yeah. Okay. I'm predictable. Okay. So what's the probability that the student likes pizza? Well, how many people like pizza? 14. 14 out of how many people total? 25. And that won't reduce, so that's our probability. 14 out of 25. Okay. Now let's try B. Likes pizza, given that he or she likes iced coffee. Okay, so let me go ahead and do this. I'm going to go ahead and use the notation that we have for conditional probability. So I'm going to say the probability of pizza given that they like iced coffee. Or you can even write it out if you want to. I'm just using the letters of the sets. So if I were to go ahead and apply the formula to this, then what I need is the probability of the intersection And what am I going to divide it by? The probability of liking pizza or the probability of liking iced coffee? There you go. Whatever's given, that's what you always divide by. Okay. Well, what's the probability of liking pizza and coffee? Okay. So let me do this down here a little bit. So we know that 6 out of 20 divided by, or 25, I don't know why I put 20. 6 out of 25 divided by. Now, the probability of liking iced coffee. 16 out of 25. Okay. So is everybody okay with how I set those up? What do we do if we're dividing by a fraction? You multiply by the reciprocal. So flip that up. So 6 out of 25 times 25 sixteenths. And we can see right away those 25s are going to cancel. So think about it. You remember we said a second ago that conditional probability changes the what? Changes the total. It changes the sample size. We're looking for how many people like pizza, knowing that they already like iced coffee. Okay, so we're not looking at all 25 individuals. We actually only ended up with 16. Where do you think that 16 is coming from? That's the total number of people who like iced coffee. Okay, well, how many people like pizza but also like iced coffee? 6. See, that's what the formula is doing for us. It's giving us the favorable, what we want, out of that changed sample size. Is everybody okay with that? But what is 6 sixteenths? 3/8. So there's a 3 out of 8 probability that a student chosen at random likes pizza, given that he or she likes iced coffee. How we doing? Are we ready for one on our own? Okay, well, let's try this next one. Let me try to erase that again. There we go. In a class of 40 students, 34 like bananas, 22 like pineapple. So we got bananas and pineapple. If I had a choice, I'd go for bananas. I find them very appealing. Okay. Anyways, the only thing I could do with a pineapple is tropic like it's hot. So tropic like it's hot. Now come on, you got to give me credit on that one. Thank you, Kate. I appreciate that. Anyways, and 2 dislike both fruits. A student is randomly selected. Find the probability that the student, and then we have 4 questions. Okay. All right, so I'm going to give you a couple of minutes to not only fill in the Venn diagram, but also to run through these 4 questions. Okay, interact with your villain buddies. Make sure you're getting the same answers. If not, maybe you go ahead and discuss it. But at the end of which, I'm going to call in some folks to help me out with this. Okay. So think about, for this particular scenario, if we don't have the intersection, what do we at least know? Do we know how many people would be in the union? We're a little more than 16. Now we've got 40 people in the universe, but what about 2 of them? Okay, we know that 2 of them don't like either. So the union of the 2 sets has to total what? 38. Okay. So think about how we would fill in. We would start with one crescent region, whether it's bananas or pineapple. Why did I put in? I don't know why I did that. Let's just say in is pineapple. There you go. That's odd. That's very odd. Or, Amy, would you like me to change it? Okay. Okay, there you go. That's been 2 minutes. Do we need another minute? Okay. I'll give you another minute. How many people at least have the Venn diagram filled in? Okay, good, good, good. All right. So what's really important here is the probability. So let's make sure we have that filled in. Let's talk about that. Now we said that two people like neither. So that means that the union of the two has got to be 38, right? Oh, didn't mean to do that. Okie dokie, then I'll just do this. Okay. Now, we don't know how many people like both, so let's go ahead and start here. I know that the total is 38, so how many people like bananas? Okay, 34, so I know that this 34 plus whatever that is has to give you 38. So how many people only like pineapples? Only 4. So see, now I can start to work backwards. How many people like pineapples? Okay, now the 16 is for the number of people who like both. Because there's 22 people who like the pineapples. Oh, it should be. Joey misled me. There we go. And now how many people solely like bananas? 16. That's where the 16 goes. There we go. How many people got that correct? Okay. Now, you don't even have to start here. We figured out solely the number of people who like pineapples first. Could we have found that 16 and worked backwards? Yeah, yeah. Does anybody want me to show you that? No? Okay. So let me give you another minute or two. Let's go ahead and answer those probability questions. There we go. So remember, only C and D are conditional probabilities. The other two are just your normal simple probability. Okay, now let's just go ahead and list the answers, and then we'll go back and talk about those that we need to. Find the probability the student likes both fruits. We should have gotten 9/20. Likes at least one fruit. We should have gotten 19/20. Has anybody found C? Find the probability that the student likes bananas, given that he or she likes pineapples. Carla, what do you think? It is 9/11s. Good job. And D, what's the probability that the student dislikes pineapple, given that he or she likes bananas? Okay, Cortland again. Oh, you're so close. Not 9/17. I got 8/17. There we go. 8/17. Okay. Now, which ones? CD. How many people did really well on AB? Okay, so not a lot of hands going up over here. Is there anything I can do? Good feedback. Okay. All right. So let's move on to C then. If you do have a question, you'll please ask me. So find the probability that the student likes bananas, given that he or she likes pineapples. So for C, the probability of liking, bananas, given likes pineapples. Or I'll stick with N. I don't know why I put that in there, but I guess I'll just keep it. Why not? I see a pineapple, I think N. I have no idea what that means. Okay, so how would this be according to the formula? The probability of their what? B intersecting N divided by the probability of B or the probability of N? N. It's always the probability of the given. Okay. So let's see here. Well, the probability of the intersection, we know that 18 people like both, but 18 out of what? 18/40 divided by. Now the probability of liking pineapple, 22/40. Okay. And when we're dividing by a fraction, we multiply by the reciprocal. And I'm just going to go ahead and keep it as is so that they can cancel out. So 18/40 times 22/40. I just said it and I didn't do it. 40/22. So that those cancel. And what is 18/22? That is your 9/11. Okay. All right. Questions? Okay. Now let's take a look at D. Let me do this down here. So the probability that the student dislikes pineapple, given that he or she likes bananas. So the probability of disliking pineapple, so I used the complement notation for that. Okay, or again, you could write it out if you want to. Dislikes pineapple, given that they like bananas. Okay, so this would be the probability of the complement intersecting B over the probability of B. Okay, so let's go ahead and use the Venn diagram to help me out with this. What does the complement mean again if you dislike it? Everything outside. But I'm looking for the intersection of that with what? Okay. So what's the only overlap they have? 16. So I'm looking at 16 out of what? 40 divided by. Now I want the probability of liking bananas. How many people like bananas? 34. Okay. So I don't know what I was thinking. 34 out of 40. And once again, we're dividing by a fraction, so what do? So 16/40, we're going to flip this guy over, times 40/34. 40s cancel. Now I'm looking at 16/34, which is what? 8/17. Okay, questions? Anybody not sure where I'm getting any value from? Anything I did? Okay. Well, let's see what else we got here. Independence. We've talked a lot about mutually exclusive, which we're going to bring up again in just a moment. But independence, two events are said to be independent if the probability of event B occurring is not influenced by event A occurring. Two events, A and B, are independent if and only if the probability of A given B equals the probability of A, and the probability of B given A equals the probability of B. Remember, we said a while back that when we first started looking at conditional probability, it's not reversible. It can be reversible occasionally, but more often than not, when you switch it, it's not going to give you the same outcome. So A and B are independent if and only if the probability of the intersection is equal to the probability of A times the probability of B. If you know that two events you are dealing with are independent, you can use this little formula right here. All right, so we got some little words of wisdom to live by. The definition can be used to decide if two events are independent. However, as a rule of thumb, if two events are physically independent, then they will also be statistically independent. So think about if I take a pair of dice and I just throw them on a table, does the outcome of one, is it in any way influenced by the other? No, they are physically independent, so therefore they are statistically independent. Okay, we actually got a problem like that coming up in just a minute. A couple notes. Never assume that two events are independent unless you're absolutely certain that they are. How can you tell if two events are independent? If they're physically independent, then they are mathematically independent. That's a big one. Okay. 3, make sure that you understand the difference between mutually exclusive and independent events. Mutually exclusive means that the events A and B have nothing in common and there is no intersection. Independent means that the outcome of event A will not influence the outcome of event B. Mutually exclusive means there is no overlap. There are no identical favorable outcomes that could occur. Okay. Number 4, independence can be extended to more than two events. If events A, B, and C are independent, then we have this right here. So like I said, it's just an extension of this rule that we just brought up. Okay, now 5. When do I add the probabilities and when do I multiply? Well, I'm glad you asked. If you're asked to determine the probability of one event or the other occurring, you add their individual probabilities. If you're asked to determine the probability of one event and the other event occurring, you multiply the individual probabilities. So those words, they're connecting directly back to our sets lesson. Or was the what? Union. And was the intersection. So one really useful way to visualize these possible scenarios you have, we've been using tree diagrams, right? So what's important here, if you follow a particular branch, each branch represents an intersection. Okay, and it's not just that one here. With this tree diagram, I've got 4 possible outcomes, right? So a second intersection could go right here. Following along a particular branch, that's going to be an intersection. So you would multiply to get the outcome of that branch. But now let's say you have some scenarios, okay, where the multiple outcomes are what you're looking for. So if more than one branch gives you what you're looking for, that's when you go ahead and add those values. That's the union. Okay. So the intersection is to follow along a certain branch. The union is to take all of those that are necessary and add them together. All right, I know that seems a little strange, but once we get an example, I think it'll be a little better. Okay. So let's try this one. 2 fair dice are rolled. Find the probability that 2 even numbers will show up. Okay. Well, let's say we roll the dice. Let's say this is the first one. What's the probability of getting an even number? Okay, 3 out of 6. Okay, let's say we roll the second die. What's the probability of getting another even number? 3 out of 6. But if I want to know the overall probability of rolling 2 even numbers, I'm going to multiply these together. Okay. So what would that end up being? 936, which is 1/4. So you have a 1 in 4 probability of rolling one pair of dice, or just 2 dice, and ending up with 2 even numbers. So if you do it 4 times, it should happen at least once in the 4 throws of the die. I was hoping that we'd get to this problem before the bell. We actually don't have a whole lot left. So we'll go ahead and stop there for today. Does anybody have any questions so far? How are we feeling on probability? Is the conditional getting a little better? Okay. Don't worry, we're going to get to practice it. Okay. All right, so we will finish this up tomorrow.